Evening. Welcome, everybody. Thanks for joining us. My name is Roger Siegel, and I'm coming to you live from Sarasota, Florida, and you're tuned into AP Physics, Electricity, and Magnetism. And my co-teacher tonight is, as always, Kristin. Hello, Kristin.
Hello, Roger and everybody. Like he said, my name is Kristin Gonzalez-Vega, and I teach at Reedy High School in Frisco, Texas.
All right. Well, let's get started with some physics. It's a beautiful Tuesday afternoon. Okay, so we're going to start here. And the lesson for today is electromagnetic induction, including Lenz's law and Faraday's law. And so we are actually getting into the last unit, which, well, we'll contrast that with the previous work in a minute. Again, I'm Roger Siegel, and Kristin is joining me from Frisco. And we wanted to let you know that the material we're covering today is not material that you're going to be tested on the AP exam this year. This is material that the colleges have told us that they want you to be exposed to, and they're aware of the situation. So we're going to give you as much as we can about this and get you a good background so that when you get to college and someone asks you about a magnet, you don't feel totally clueless and you'll be ready to learn more about that. Great. All right, so the first thing I want to do here is review and what we've done. And if you have tuned in or if you haven't, what we've been covering so far is Unit 4. And that is basically two halves, I would say. There's two parts here. The first part is where we're looking at what is the result, what does a magnetic field do to moving charges and to current carrying wires. And then the second part is asking the question, how do I get a magnetic field? And if I have a certain current, how much magnetic field does it produce? And so that was Unit 4. And now today, we're going to start to talk about magnetic induction, okay? Now, I want to go ahead and actually, get back here because I want to look at you guys. So magnetic induction is when we have, is actually how electricity is created. So electricity is ubiquitous, we take it for granted. But when we flip on the switch, that electricity got created somewhere, it got generated. And it got generated in a power plant. And that electricity came to your home. So how does that electricity come about? How does it get generated? So that's the phenomena called electromagnetic induction. And that's what we're going to study today. So Kristin has a really cool display here that she's going to show you. And so I want to let her take it from here.
Okay, so let me switch over here and show you what I have. I have set up a slinky, one of those big long slinkies, and I have connected the slinky up to an ammeter. So no battery, nothing else attached to it, simply connecting the slinky right to my ammeter. And as you can see right now, there is no current going through that slinky. But if I take a magnet here, bar magnet, and I place that north pole of that magnet towards my slinky, I want you to notice what's happening to the current here. And I'm going to zoom in just a tiny bit so you can see that just a little bit better. Okay, so I'm going to hold down the side of the slinky just so that it doesn't get attached to it because it is a magnet and this is metal. So as I bring that magnet into that coil, you can see that it's changing. And you can maybe notice what is the sign of that current when I bring the magnet into the coil and when I take it out. And then you're looking at a mirror view of it, but you can still see that it is going negative when I put that in. But then when I stop and it is in the middle of the coil, look, it's zero current again. And then again, when I bring that magnet back out, it became positive. When I don't move it, that current's back to zero. So we can kind of move in and out, and we can see that current flipping back, positive, negative, negative, positive. Okay. Is there anything else with that you wanted to see, Roger?
No, I think that's great, but don't put it away because we might come back to it.
Yeah.
Okay, great. Thank you. All right, folks. So let's go ahead and look at this, and we're going to look at a simulation. We might look back at Kristin's demo, and we want to look at this a lot of different ways. So I want to go ahead and get my screen up, share it with you guys again. So we're back here, and I'm a little bit ahead of where I am. I want to go back to this. Okay, so there are two concepts that we've got to get our brains around that are going to allow us to understand electromagnetic induction or generating electricity. And those two concepts are first magnetic flux and then magnetic induction. Now, flux, I hope you remember the word flux, not just from the flux capacitor in Back to the Future, but hopefully earlier in the year, you studied flux and your teacher, you learned about electric flux, okay? And so electric flux is just the electric field that is perpendicular to the surface of a solid dotted with that area. And so this is what we learned earlier in the year. The flux, and this is our phi sub E, electrostatic, is equal to the closed surface integral of E dot dA, all right? Now, magnetic flux is basically the same thing. First, take a look at these two take a look at these two equations. They're almost identical. The E and the B are of course different. Something that you can't see though that is different is this is a three-dimensional structure, a solid that is truly three-dimensional. This is the surface of a loop of wire. And so that'll make sense as we get into that. Let's see how that works. Okay, so the first concept is flux. The second one is electromagnetic induction. And so electromagnetic induction means generating electricity. You just saw Kristin do that. And so here's what we're going to say about electromagnetic induction, and then we're going to do some demos of that. So a current is induced in a loop of wire if the magnetic flux through that wire loop changes. All right, so let's take a look at that. I'm going to pull up a simulation, and if you're not familiar with PHET, these are some of the best physics simulations out there. They're just really, really good. And so I'm going to open up the PHET window and show you this simulation. And this one is called Faraday's Electromagnetic Lab. I don't know if you can see this up here. And so this shows us an animation of a magnet, and you can see that we've got the compass. But what this simulation allows me to really do is to see the magnetic field. And so I can see the field. You see, I can turn it off. Magnetic fields, of course, are invisible, but this allows me to see that magnetic field, okay? Now I'm gonna go to the next simulation, and this is called a pickup coil, okay? Now, notice that there's the magnetic field. Now, the first thing I wanna talk about around this pickup coil is, let's just talk about the flux first. I'm gonna try and just capture this for a second because it'll help me to draw a little bit on here for you guys. So bear with me for a second. So you can see here that we've got this magnetic field, and this magnetic field comes out of the, oh, that's not going to be good. Let me go ahead and move this, try this white. Let's see, that's what we want. All right, so we've got this magnetic field that is coming through this loop, okay? And it literally is passing through that loop. Now, when we multiply the perpendicular component times the area, and we add up all that area, that's the flux. So the first concept is just getting what the flux is. The second concept is getting how is it changing. Okay, so let me shoot back to the simulation here. And so watch what happens in this simulation if I move the magnet near the coil. If I put it in there, nothing happens. But if I shake it, I hope you can see on your videos that we're getting a light bulb lighting up. And why is that? Because I'm changing the flux. I'm changing the flux through this coil, okay? And so that is what we're looking at. Now, a couple different ways to change the flux. One way to change the flux, well, let's go and just review for a second what is flux. We talked about that a minute ago. So flux is the area times the B field, all right? So let's go ahead and see this. We've got our area here. Let me get this back here. Here's our area, okay? And here's our B field. Now, how do we change that? Well, one way to change the flux is to move the magnet. That's called an electromechanical change. Or we could move the coil, because that also changes the flux that's going through my loop. Or instead of doing that, I could make the coil bigger. Now, you might not see this. I don't know how fast the refresh rate is on your computer through this recording, but I really want you to get to this simulation and give it a try, the PHET website. Watch what happens. If you can see, when I change the area of the loop, I'm also changing the flux. And I don't know if you can see it, but we are getting a little bit of light up here when we do that. So it's kind of simulating for us that we're creating light. Now, most generators actually have this kind of structure where we have a magnet that is spinning near a coil or inside a coil. And that is changing the flux, and that's what's causing our electric generation. All right. So let's go ahead and go back to our PowerPoint, and let's see what we have. So here is flux, and I want to talk about electromagnetic induction. What changes the flux? Okay, well, the flux is B dot dA. So if either B changes or A changes, then the flux changes. And by the way, also the angle could change. Now, traditionally, most AP Physics C E&M questions have to do with either the B field changing or the area changing, and we're going to look at both of those. Okay, so is there a change in the magnetic field? That would change the flux. Is there a change in the area? Is there a change in theta? And that is a mistake. So we'll cross that out. All right. All right, now let's take a look. The second thing I want to get to is Lenz's law. And Lenz's law is going to tell me the direction of the induced current. So remember, if the B or the A changes, I'm going to create a current in a loop. What is the direction of the current? Now, I'm going to read to you what it says on here, knowing full well that this is one of the most convoluted sentences in all of introductory physics. But we're going to play with it. You're going to see it does make sense after a while. All right, so Lenz's law says an induced EMF produces a current whose magnetic field always opposes the change in magnetic flux which caused it. That's a lot, right? It refers back to the future and oh my goodness. So let's see if we can get a handle on what this looks like, okay, and what this is. So I'm going to show you, I'm going to bring up my doc cam here, and I'm going to show you this slide. It says Lenz's law in action. And we're going to zoom in a little bit because you want to really see this. So let's zoom in. Lenz's law in action. What is the direction of the induced current in the circular loop due to the current shown? All right, now let's look at this. We have here on the top left, we have a current that is flowing to the right, and that current is increasing. Now, I know from my right-hand rule, and we call it the grip rule, that if I have a current and it's moving to the right, I'm going to grip that wire with my hand or pretend that I'm gripping it, and my thumb is going to indicate the north I'm sorry, the direction of the current, my fingers are going to indicate the direction of the magnetic field. So let's take a look at that. So hopefully you can see the magnetic field is coming out of the page on this side of this wire, and it is going into the page on the downside of the wire. Okay, so now we've got a current that is coming, going into the page, all right, because of the direction here. Get a little bit closer if I can. All right, now, what does that mean? Well, that means that there's a current, a B field coming through this wire. Of course, it gets smaller as you go further away, but it's going through this loop and it's increasing. So my B field is coming, going into the loop. And I'm also going to say that B dot is into the page. That is, the change is into the page. As this current increases, this magnetic field into the page increases as well. And so as this magnetic field increases, B dot is into the board. That means B induced is out of the board, out of the paper. That means that there's going to be an induced EMF going this way, opposite of these guys. And that induced EMF, I'll go ahead and draw it here, dot circle, that's coming out of the board. That's my induced that's my induced B field. And I know that if I have a B field that is coming out of the loop, that B field, I'm going to pretend, again, the grip rule, I'm going to grab this loop on the left-hand side and my thumb indicates the direction of the current. And so the current in this loop is going to be going clockwise, counterclockwise. Let's look at this one. The current is decreasing. I'm going to use the grip rule, and that means that the B field is coming out of the page here and going into the page here. Now, in here, I have a B field that is out of the page, but the B dot, the change in B, is into the page. It's the opposite of that because the field is coming out of the page, but it's getting smaller. So if B dot is into the page, Lenz's law says that B induced has to be out of the page, okay? And so we've got this out of the page current that's getting smaller. It's going to create an out of the page field that's getting smaller. It's going to create an out of the page field. I'm doing the grip rule. And so again, we're going to get a counterclockwise current according to Lenz's law. Okay, two more real quick, and then we're going to throw it back to Kristin. All right, on this one, we've got an increasing current. And I'm going to use the grip rule. The grip rule tells me that my B field is coming out of the page here and going into the page here, and which means that we have this. And so B is out of the page. B dot, the change in B, we know that that's increasing. So it's B dot is out of the page, which means that B induced is into the page. And so we're going to get an induced current, an induced field, sorry, that is this way. And then you ask yourself, what current produces that field into the board? And I'm going to use the grip rule, and I put my hands into the ring and I grip, and that shows me that I'm going to get a clockwise current. And so the last one here we have is we've got the current is increasing. Grip rule tells me that this is coming out of the paper here. And this is going into the paper here. Make sure that you can see why this is with your grip rule. And we know that since I is increasing, we've got a B field that is out of the paper, and that B dot is, is into the paper, and B dot it's getting bigger into the paper, which means that B induced is going to be out of the paper. And so we will have this induced B field coming this way, and you ask yourself, what current would cause a B field in that direction? And again, that is the counterclockwise a la the grip rule. Okay. Kristin, are you available yet?
Yes.
Okay, didn't see you, so I wanted to make sure you were still around. All right, we're going to throw it over to Frisco, Texas, and Kristin's going to get us through a few practice problems, getting us ready to understand how the induction rule works and how Lenz's law works. So take it away, Kristin.
All right, thank you, Roger. Yeah, so we are going to go back over and practice that with some practical things. And I want to review an equation that's kind of important to be able to reference back to. And that was, how did we determine the magnetic field around a long current carrying wire? So we used Ampere's law, and Ampere's law gave us yesterday that B is equal to mu naught I over 2 pi r. So that's kind of how we can see how is that magnetic field changing. So like Roger was saying, if we are increasing the current, that is how we know that we are going to increase the field. Right? I could also move my wire. So if we look at a region where I have a magnetic field and I have a loop, I can move my wire closer or further away from that. And that's going to change that R value. And as we decrease R, that's also going to increase the field. So we're kind of referencing back to that equation on how we know what's happening to that magnetic field. All right, so if we look at this example here, I have a spatially uniform magnetic field B. It is perpendicular to the plane of the page and exists in a circular region of radius r, 0.75 meters. So that is the whole entire magnetic field is that 0.75 meters. The loop of wire itself is a single loop, and it has a radius of 0.5 meters. It is in the center of that magnetic field, and the magnetic field is increasing into the page at a rate of 60 Teslas per second. And we want to determine the induced EMF in that loop. So if we look back at our equation, we know that the induced EMF is equal to, truly we can say that it's N times the change in flux over change in time. And there's a negative sign in there, and what that's going to help us tell is the direction. So the N is the number of loops. So if we only have one loop, it's 1, and then we don't have to worry about it. The only time you really want to make sure you're still looking at that is that if you have multiple loops. So if I had looking at my solenoid, right, that has multiple loops to it. But we have one loop here. And so then we also know that, well, I'm not given what the change in flux is, but I can relate that the change in flux is equal to, so I can plug in how we get the flux. So we can say that the induced EMF is equal to the change in flux over change in time, and we know that our flux is going to be B dot A. And so if we plug in and we say that this is changing at a rate of 60 Teslas per second, and it's changing into the page at a rate of that 60 Teslas per second, then I can also plug in so that is what our change in our magnetic field per time is. So that is what our dB over dt is. So the only other thing I need to plug in then is the A, and that would be that cross-sectional wire area. Only the wire, not the whole magnetic field. It's the area of that loop that is in the magnetic field. So then we can say that the induced EMF is equal to that 60 Teslas per second times the area. How do we get the area of the loop? We say that's pi r squared. So pi times our r of our loop, which is 0.5 squared. And if we solve that out, we get 47.1 volts. And if we want to say, well, what is the direction of that induced current? I'll give you just a second again to look at that. Hopefully you have some paper out and you're doing this with us this evening. So I now want to know, well, what would the direction of that be? So we want to look at which way do we have a changing magnetic field? Do we have a changing flux and which way is it? So if my field is changing and it's changing into the page, right? And my magnetic field is already into the page. So what that tells me is I have a positive change in flux. So what I like to think and tell my students is that we always are going to induce a field that's opposing the change, right? So if I have an increasing change in flux, and I want to create a magnetic field that's going to oppose that change. So I need to create a magnetic field or induce a magnetic field that's coming out of the page, that's opposing that change. So if my B field is increasing, I need to create a magnetic field that's going to decrease that change. So the way that I remember how to do this is if you are going to have your loop of wire, then I point my thumb in the direction of which way that changing field should be. So if I want a magnetic field coming out of the page, my thumb points out and my fingers are going to curl around in the direction of that induced current. So if we put our fingers out at us, we're curling around counterclockwise. Okay. All right, moving on, let's do another one. Let's look at our moving bars. This is always kind of a popular problem in electricity and magnetism type problems. So we have a conducting bar here, and that bar is sliding down without friction that is connected to two vertical conducting rails separated by a distance L and joined at the top by a resistor of unknown resistance R. The bar maintains electrical contact with the rails at all time, and there's a uniform magnetic field B directed into the page as shown. The bar is observed to fall at constant terminal speed V naught. So what we want to determine is what is the magnitude of the induced current in the bar as it falls with constant speed in terms of BLG, V naught, and M. Again, we've got one of those in terms of things, right? So we're going to be careful. So if we want to know what the induced current I is, well, the first thing I want to look at is what are some equations we can use, right? So thinking back to what we've learned today, some of them that we have learned is that our flux is equal to the integral of B dA. We know that our EMF is the change in flux over change in time. Okay, so if we also can look at this, I also know, let me use some different colors here, that what's really important here is it is constant terminal velocity. So if this is constant velocity, what should be about the forces acting on the bar? They should be balanced out. So if this is sliding down, right, we know that we have mg acting down. But if it's sliding down at constant speed, I also know that I have a magnetic force that must be upward. And so if those are going to be equal, then we can set them equal and say, well, the magnetic force has to equal mg, where the mass is big M. Remember, we always want to be careful that we're using those variables correctly because little m is not the same as big M. And we also know that the magnetic force we learned on that segment of wire is ILB, where I is the current going through it, L is the length of the bar, which is L, and B is the magnitude of that magnetic field. And so if I want to know what current is, I is going to be equal to mg over L times B. Okay, another thing I kind of want to look at while we're looking at this is what exactly is happening on the bar, because there's another equation that we can use for the induced EMF of a sliding bar that's pretty common and is a good one to know. And if we look at this bar, and I zoom way in on this bar, well, if there is current traveling through that bar, we know we have charges within that bar. There's positive charges and there's negative charges in that bar. And we can say that if we have positive and negative charges in there and those charges are moving, right? Maybe they're evenly spaced out throughout, but if I just look at one of each of those, these charges are moving. Each one of these, because the bar is moving down, has a velocity down that is moving at the same rate, right? So if these charges are moving and they exist in a region where there is a magnetic field, what do moving charges experience? They experience a force. So if we use our right-hand rule and look at which way those individual charges are being forced in that bar, well, let's take the positive charge first. The positive charge is moving down, and I kind of like to tilt mine. But so if the velocity of those positive charges is down and the magnetic field is into the board, well, then those charges are going to experience a force this way. And we know that we could do either the left-hand rule or we do the right-hand rule and swap it. Those negative charges are going to experience a force to the left. And so we're going to get this separation of charge within that bar. All of those positive charges are going to be forced towards that right side. All of those negative charges are going to be forced to the left. And what happens when we get a separation of charge within a material, a conductor? We're going to get an electric field. So within that bar, we're going to have an electric field. Which way do electric fields point? Away from positive towards negative. And so these charges are going to keep moving or separating in that rod until we get the electrostatic force on those balanced out by the magnetic force. Oops, Fm. And how do we get what that electrostatic force is? Well, the electric force on them is Q times E. And we also know that the magnetic force on a moving charge is QVB. V is the velocity. Well, our charges cancel out, and we can say the electric field that will be formed between those two is going to be equal to the velocity of the bar times the magnitude of that magnetic field. So sometimes that might be useful information, but maybe not. Maybe I want to know about potential difference that's going to be induced because of that separation of charge. So what is the potential difference in the bar there? Well, we can relate to that to field because we know that the electric field is equal to the potential difference divided by the distance. So I can put in that the E is equal to the potential difference, capital V, divided by the distance. And what's that separation distance going to be? It's going to be L, the length of that rod. And so that will equal VB. And so if I rearrange for what that voltage is, and really let's call it that induced EMF, it's going to be equal to B times L times V. And this is an equation that we use a lot with induction with these moving bars or moving wires that we can reference back to. And so I'm going to even do a little bit more of an extension on here. Let's find what the induced EMF is, and let's find what that unknown resistance in the resistor is. So we can say that that EMF is B times L times V because we know all those things. Those were all given to us. But we can also use Ohm's law because we know that induced EMF is equal to IR. I know what my I is. It's mg over LB. And so I know what my EMF is, so I can say, well, B times L times velocity is equal to my current, which is mg over LB times R. And so I can find what that resistance is. So resistance will be equal to, if I multiply out, I get B squared L squared times the velocity divided by mg. So lots of things that we can do with these moving bar problems. They're super cool. Let's also find what the direction of the current must be in that bar. So if we want to find what the direction of the current is in this bar, then we can look at, well, if we are changing that, how can we find what that direction is? Well, if I look at these charges and I want to know if this is moving down here and those charges are being forced through, which way would that current have to be? So if it's maintaining that constant velocity and I know that that force has to be upwards, then we can say that if the force is up on that moving bar, then the current has to be going around through it this way. Okay, and then we've got one more here. Oh, two more, sorry. So let's look at our rectangular loop. And so the rectangular loop of wire here has dimensions W and H. It's approaching a region where there's a magnetic field, again, into the page. And the magnetic field extends from W here to 3W. So it has a width of 2W. So that loop can go all the way into that field and it can be all the way out. So we want to look at if the interval after the right-hand side has entered the loop, but before it is totally into the field. So if we sketch that out, then we know that that leading edge is inside it only. What would happen if we have all of it inside, right? Well, we can look at that too, but we only want to look now as if part of that wire is in that field, then what's going to happen? So if we say that we want to know what the induced EMF is, well, we know that induced EMF is going to be equal to that same thing that we used last time. I can go back and say that it's BLV. So our magnitude of the field is B, our velocity is V, and the length of that is going to be affected is that H. So we can say this is B times H times V. And in what direction will that be induced? Well, as this is approaching that field, then it is going to have an increasing flux. So we want to create a magnetic field that is going to oppose that change or is going to be into the page. So, or coming out of the page, sorry. So if it's coming out of the page at us, right? If I point my thumb, I want that magnetic field due to that induced current to be out of the page, then my fingers are going to curl around in that loop counterclockwise. So that current is going to be induced upwards through that part of the loop. And lastly here, if we look at our loop of wire that has a magnetic field into the page, sometimes we're given some things that are changing, right? So we know that not always nice constant things, that we have things that are changing. So the induced EMF in the loop is given by the equation that the EMF is equal to B times A times T to the 1/2, where B is a constant, right? And A is that area of the wire. So we want to look at what could be the time varying magnetic field. So we want to solve for the magnetic field and what it could be due to this changing magnetic field or the changing EMF. So if we go back and we know again that our EMF is our change in flux over our change in time. And we also know that our EMF here is equal to our B times A to the 1/2. Well, I still need to plug in then how we find that change in flux. So really, I can say that this is d over dt times B times A dot A, but it's perpendicular, so we don't have to worry about that angle, equals BA to the 1/2. So if I want to solve for B, I need to integrate both sides. And if we integrate the right side, we're left with that BA. And if we integrate the right side here, they said that B is a constant. Oops, I'm missing a T here. Sorry about that. So if we integrate that, it was like, we have all constants. So we have B and A, which are constants. So if we pull those out, really the only thing we're integrating is that T to the 1/2. And so what we're going to get here is we're going to get T. If I add 1 to my 1/2, I get T to the 3/2 divided by 3/2 or times 2/3, still times my B A. Okay, so if we look here, we've got an A on both sides, so those A are going to cancel out, and we get that B could be 2/3 times B T to the 3/2, which if we look here is choice E. Okay, so we're going to turn it back over to Roger, and he's going to work one more really fun problem with us.
Okay. Well, thanks so much, Kristin. I am excited about this problem. She's right. This is a fun problem for me. So this is one of my favorite ones. And it just it shows so much what's so great about AP Physics C. I could go on, but I'm running out of time. Okay, so let's look at this. This is actually the second part of the problem from the 2018 exam. And I actually ended up grading this exam in 2018 in Kansas City, this question. But anyway, so you can see that we've got a wire, and the current in that wire is decreasing linearly as a function of time. And so that's our current, 2I times the quantity 1 minus, oh, you probably can't see this, can you? I'm sorry. Let me shoot that up here to you guys. Okay, sorry about that. All right, so as I was saying, this is just, is one of my favorite problems. So we have this current here, and the current is going down. This I2 is some constant I times 1 minus KT, where K is a positive constant. So if you want to imagine what the current looks like in that wire, well, it looks like this. Here's I naught right there, and it decreases linearly like that. So the current is going down. All right, but we know the current is at first moving to the left. And so I'm going to use the grip rule. I'm going to put my thumb to the left, and it shows that up here that the B field is into the board, and on this side the B field is out of the board. And I'll just put these here, but really what I'm interested in is what's happening here. And so I'm going to make these smaller. Now you can probably imagine why I'm making them smaller is because, as you may remember from yesterday, the magnetic field here, B, is mu naught I over 2 pi r. And so what that means is, as I move further away from this wire, the magnetic field gets smaller and smaller. All right, now the first question says, what is the direction of the induced current in the loop? So let's look at this. We can see that the current in this loop, the B field, I'm sorry, is coming out of the board. Wait a minute, I'm sorry, the B field is going into the board, thank you. And it is decreasing. We said over here that the current is decreasing, so that means the B field is decreasing. So I've got a B field that is into the board, but its change, B prime, is the opposite because it is into the board but decreasing, so the change is out of the board, which means that the induced current has to be the induced magnetic field has to be into the board, which gives me a clockwise. So I'm going to put clockwise current here. Okay. So again, we've got a B field that is into the board and decreasing, and so what we will induce is we'll induce a magnetic field into the loop, which gives me a clockwise. Now, let's do the flux and see if we can get out of here at a decent hour. All right. Now, the flux is, remember, the flux is how much B field is inside of this loop. And remember that flux is phi magnetic is the closed integral over a surface, not a solid, but a surface of B dot dA. All right, now, I love this problem because you can see what happens here. This B is mu naught I over 2 pi r, where r is the distance from here. Let me go ahead and do this in a different color. Let's go ahead and get that distance. And that r is that distance from here to here. And so we have the B field is mu naught I over 2 pi r. Now the area, the dA, is kind of cool. Check this out. As I go from here to here, the B field goes down. And so I've got to multiply the B field at every point along here because it's not constant. And so what I'm going to do is my dA is going to be this length here, L, times this tiny little width, dr. So I'm going to write that as mu naught I over 2 pi r times L dr. And where am I integrating from? I'm integrating from this distance d to d plus w. So that's going to be d and d plus w is what we have there. Okay. Now, you may recognize this. I'm going to write it again, sorry, because you can't see anything now. So we're going from d to d plus w. And we have, again, B, mu naught I over 2 pi r. That's the B. The area is going to be L times dr. And that'll give us the flux. All right. Now, notice we know that I changes as a function of time, but we are integrating as a function of r. We're integrating in space. So that I can come out front with the mu naught. So that's going to be mu naught I L over 2 pi r times the, 2 pi times the integral of dr over r from d to d plus w. And so I'm sure a lot of you remember that the integral of 1 over r dr is the natural logarithm of r. And so what we get is mu m is equal to mu naught. I is what we said it was before. And so that's going to be I naught times 1 minus kt. Okay, mu naught I, which is I naught over 1 minus kt, times L, okay, over 2 pi. And then finally, what I have is, remember, I have a logarithm here. And so I'm going to say that that's ln of d plus w over d. And so this now is our flux, okay? And let me check that against what I have before. It looks right, okay. Now, we've just found the flux, and I want to, again, pull us back to that. What did we find? We found the amount of B field through this area, okay? Now, the last part is the how much, if the resistance in the loop wire is R, okay, how much induced current. So I know that I is equal to V over R, or that's 1 over R times the EMF. Now, that can be written as 1 over R times d dt of phi sub n, the time rate of change of the magnetic flux gives me the voltage or the EMF. So I'm going to write that one more time, 1 over R, and then I'm going to write d dt, and I'm going to rewrite everything that I wrote up here for the flux, okay? And so we're going to take the d dt of this flux, which is, and I'm going to write, let's see, we have mu naught, I naught, L over 2 pi ln of d plus w over d times 1 minus kt. Now, that is the flux that we just found. All right, I just rewrote it. And so at this point, what we want to do is we want to take the derivative of that, okay? And so I'm going to go ahead and I'm going to write this up here, and I'm going to say 1 over R, the derivative of this. Now let's look at all these terms, and we're taking the derivative with respect to t. There's no t here. There's no t here, okay? There is no, I'm sorry, I forgot. There's a 2 here. I wanted to go back. I kept thinking I lost something. Is there a 2 there? 2 I naught. Yes, yes, yes. So sorry. Okay, there's a 2 there. I knew there was something that I lost. Okay, that makes me feel better. Now, so we have 1 over R, but let's look at this. What terms have a T in? This is the only term that has a T in there. So I'm going to say 1 over R times mu naught I naught L over pi. The 2's are going to cancel, these 2 2's. We have the natural log of d plus w over d times the time derivative of this term, which is just going to be negative k. Now, the negative just tells me the direction of my current. And so that is where I end up, and we'll usually find the direction using, well, we already found the direction using Lenz's law. Okay, now, I know that was a long one, and I really appreciate you, being patient with me as I go through that. Now let's zoom out, and before we leave, I just want to say one more thing about this problem. Why do I love this problem? I love this problem so much because it shows the power that you students have to use calculus so powerfully, so freely, because check it out. First, you're integrating with respect to space, and then you're differentiating with respect to time, all in the same problem. That is some super advanced calculus, and I want you to be proud of yourself for following that. All right? All right, so we have really gone the gamut today. We've gone through the whole thing. Let me go ahead and take us out of here. Debrief. So this is what we tried to do today to help you understand magnetic flux and magnetic induction. And maybe next time you turn on the light switch, you'll go, hey, some induction just happened somewhere. We want to thank you so much for the hard work you're doing, following along, and we hope these are helpful. So keep tuning in, keep up the great work. So from Sarasota, Florida, and Kristin?
From Frisco, Texas. And Roger, I just want to make one correction really quick because no, it's me. I made a mistake real quick.
Go ahead.
Can I drive real fast?
Let me go ahead and get out of here. Sure. Okay, give it a try.
This is when we know it's live TV, guys, right? This happens in class. I said the wrong thing for the direction of the current in the bar. I don't know what I was thinking. It should be to the right, and let's see why. As this is moving here, this is what our loop is. And so as this is moving, let's say the bar is down here, my area is bigger. So that flux is that area is increasing in that equation that the flux is B dot A. So if that area is increasing and my flux is increasing, I'm going to induce a current that's going to decrease that field or be into the page. The only way I'm going to get a field into the page is if I'm going around clockwise. Out of the page is if I'm going around counterclockwise. See, I almost did it again. So it really should be to the right. And I apologize for that, but it's to the right.
All right, Kristin. Well, I can honestly say, I don't think I've taught a day without making a mistake. So that's the way it happens. Anyway, thank you so much for tuning in. Again, we hope these are helpful, and we'll see you tomorrow night.
Good night.